Here they're wanting us to find angle A, side A, and side C. So let's begin by finding angle A. So we know angle C is 90 degrees. We know angle B is 62.8 degrees. And we know that the angles add up to 180. So we can either do angle A plus angle B plus angle C equals 180. Or being a right triangle, we can use the fact that these two angles are complements. So these two angles add up to 90. But either way we do that, we would get, we could simplify the left side and get A is 152.8 degrees. And then if we subtract that from 180, then what we're left with should be about 27.2 degrees. 27.2 degrees for angle A. So now let's say side A. So we want to use one of our angles. It could be the 27.2 degrees, or it could be the 62.8 degrees. I'm going to use the one that was given just in case I subtracted wrong to get angle A. And then side A that we're looking for is adjacent to 62.8. The side that we know, side B, is 132. So which trig ratio involves an adjacent side and an opposite side? Well, that would be tangent. Tangent of that angle is the opposite side divided by the adjacent side. Tangent is opposite over adjacent. So we can solve this for A. We can multiply both sides by A to make the A's cancel on the right. And then we can divide by tangent 62.8 degrees to get A by itself. So when we do that, I have to make sure our calculator is in degree mode because our angle is degrees. So 132 divided by tangent of 62.8 degrees, we get about 67.8. 67.8. Now once we get that side, we could use the Pythagorean theorem to find the third side once we know 2, since this is a right triangle. Or we can just use trig to find the other one. So we could say from 62.8, C is the hypotenuse, 132 is opposite, so the trig ratio that involves the opposite side and the hypotenuse of 62.8 degrees is opposite over hypotenuse. And like we did on the previous one, we could multiply both sides to get rid of our fraction. And then we can divide to get C by itself. So C, we got 132 divided by sine of 62.8. So about 148.4. So that gives us A, C, and angle A. Notice that angle C was the largest angle. It's 90 degrees, so side C has to be the largest side. All right, this one, they want us to find the missing pieces. So side B is 200, so that's the side across from angle B. Side C is 450, that's the side across from angle C. And they want us to find the rest of the pieces. So to get side A, since we only know one angle, we would have to use the Pythagorean theorem. So A squared plus the other side squared equals the hypotenuse squared. So A squared plus is that 40,000 equals 450 squared, 202,500. Subtract 40,000 from both sides. That would give us 162,500. So A would be the square root of that. So we take the square root of that. Let's see, I don't know how many decimal places they wanted us to go, but that's about 403 units. To one decimal place, that's 403.1. Once we have that third side, now let's find angle A. So I always like to go back and, if possible, use what we were given. We were given those two sides. So if I want to find A, 200 is adjacent to A, 450 is the hypotenuse. So that means that cosine from angle A is 200 over 450, adjacent over hypotenuse. So if we use the inverse cosine button with that ratio, that will tell us what A is. So 200 divided by 450, take inverse cosine of that, and that's 63.6 degrees. 63.6 degrees. Once we have two angles, we can find the third one just by taking them away from 180. Or, if we want to, then we can use trig to get B. We are given 200 and 450, so 200 is opposite, 450 is hypotenuse, which means that sine from B is 200 over 450. Opposite of B over hypotenuse. So that means inverse sine of that ratio will give us B. So 200 over 450, take inverse sine, and that's about 26.4. And if we add those angles together, notice those angles do add up to 180 degrees. Sometimes doing it this way, we might have a little bit of round off error, and they might be a tenth or so off. But in this case, adding those three angles, we do get exactly 180. Now here they talk about a zip line. The zip line has a certain length and it has a certain drop. We want to find its angle of depression. So we have to know this terminology. What is an angle of depression? There's a worksheet in Canvas that describes some different terms. An angle of depression is measured from the horizontal downward. So from horizontal downward. An angle of elevation is measured from horizontal upward. Our zip line starts here and it goes to here. We're going to pretend that there's no swag in our zip line. The length of it is 5,260 feet, and its drop is 1,259 feet. Drop, that's the vertical drop, that's perpendicular to horizontal. So the angle of depression would be from horizontal down to there. So I'm just going to call that theta. So we want to find out what is that angle. We're given the side opposite of that angle and the hypotenuse. So that's going to be sine. Sine theta is the opposite side divided by the hypotenuse. So that means theta we could get from taking the inverse sine of that ratio. So if we take our calculator out and do 1,259 divided by 5,260, and then take inverse sine, we get an angle of depression of about 13.8 degrees. About 13.8 degrees. All right, the next one, we have a 12-sided polygon that's inside a circle. So let's see if, I think this program will let me draw this. So let's see if I can find, all right, here's a 12-sided figure. And then that's inscribed in a circle. So that means that's inside the circle. There we go. And the circle has a radius of 19 centimeters, meaning from the center to the edge of the circle, that's 19. So everywhere we go from the center and touch the circle, that distance is 19. Notice if we touch each vertex of this dodecagon, if there are 12 sides, then that divides our circle into, or that divides us into 12 triangles. Well, if there are 360 degrees in a complete rotation, and we divide that by 12, then that angle of each of those triangles is 30 degrees. 30 degrees. So that's going to be true for all of them. But those are isosceles triangles. So if that side and that side are the same, so if that's 30, that means we have 150 degrees left for the other two angles combined, which if each of those are the same size, if we divide that by 2, that means that's 75 and that's 75. So 75 and 75 is 150, 30 more is 180 inside that triangle. Well, notice those are not right triangles. So our trig rules are all based on right triangles right now. So what we can do is we can draw a perpendicular bisector. Perpendicular bisector. So this angle is 90 degrees. We know the hypotenuse. If we just bisected that angle, if this full angle here is 30, then that means this angle and this angle are half of 30, so 15 degrees. And then we could have found, if we didn't already find out, we now can find out that that's 75 degrees there. So we'd already found that out by the isosceles triangle. But even if we didn't know that, this is 90. If that's half of 30, that's 15, and then we could deduce that that's 75. So I'm going to enlarge that little triangle there. 19 centimeters here, 15 degrees here. Now, we're wanting to find the perimeter of the dodecagon. If we can find that distance, which is here, then if we double that, that'll give us one side of the dodecagon, and then we can multiply that by 12 to get all the way around, because we have 12 equal sides. Or we could take that distance and say, well, if each of the 12 sides are broken in half, then there are 24 of those halves. So let's just call this distance x. So we need to find this distance to eventually get the perimeter. This side is opposite of 15, and we have the hypotenuse. So sine from 15 degrees is opposite over hypotenuse. Solve for x, so multiply both sides by 19. So 19 times sine of 15 is about 4.9. I'm going to keep a couple extra decimals, 4.918. That would be in centimeters. So if we double that, 9.835 would be one side of the dodecagon. And then if we multiply that times 12, that'll be the total perimeter. So to the nearest integer, that perimeter would be 118 centimeters. Now you might say, where did this come from? I didn't straight up just double this. I kept all those decimals in my calculator and I doubled it, and then I got that. And then I kept all of those decimals in my calculator and multiplied it by 12 because we have 12 sides. So that would give us the distance around the perimeter of the dodecagon. Now the last problem that I'm going to go through right here is the trickiest problem because we're not given everything that we need directly. So we end up actually having to solve a system of equations. So we have a suspension bridge, and it has two towers, and here's our tower. Here are the towers for the bridge, and the towers have the same height. So we're on a boat out here, and when we first measure the angle of elevation, so remember elevation is from horizontal upward. So from horizontal upward, then we're looking up, we're standing in a boat over here, looking upward, so our angle of elevation is 23 degrees. But we don't know the distance from here to the tower. So then we sail 443 feet closer, so this distance is 443. And then when we measure our angle of elevation again, this time we get an angle of elevation of 50 degrees. So that produces two right triangles. It produces one right triangle that has a height called h and an angle of elevation of 50 degrees. But notice we don't know the distance to the top of the tower or to the bottom. We just know it's a right triangle. And then we have another triangle, the original right triangle, that had an angle of elevation of 23 degrees and a height of h. And we don't know any other side on that triangle. Now you might say, well, if we used, let's see, this inner triangle here, then we know a side of that triangle, and that's true, but that's not a right triangle. And so far, the only things that we know how to work with are right triangles. So what we need to do is call this distance, we could call it D. So in the smaller triangle, this side would be called D. In the larger triangle, this total distance is a combination of the 443 feet closer that we went and then the new distance from that new position to the bottom of the tower. So that total distance would be D plus 443. So notice we don't have a full side in either triangle. So we just need to write a relationship for our triangles. From 50 degrees, we've labeled the opposite side. So from 50 degrees, tangent would be h over d. Well, that has two variables. If we have two variables, we have to have two different equations in order to solve for those variables. So we can go to our larger triangle and do the same thing. Tangent 23 degrees is the opposite side over the adjacent side. If we want to, we could clear fractions. So we could multiply the first fraction by d and get d times tangent 50 degrees equals h. On the other one, we could multiply times d plus 443 on both sides to get, let's call that d plus 443 times tangent 23 degrees, and that's also equal to h. So by substitution, if this is h and this is h, then those two statements have to be equal. D tangent 50 degrees and d plus 443 times tangent 23 degrees, those two things have to be equal. So this gives us an equation that hopefully we can solve for d. Notice this equation is linear in d. Our d is to the first power. Tangent 50 degrees, that's just a number, so that's really just a coefficient. That's a number and that's a number. So we have our variable to the first power and then some numbers. So when we have an equation that has parentheses, we want to distribute to get rid of the parentheses. So we can call that tangent 23 degrees times d. That's the coefficient of d. And then we can do 443 times tangent 23 degrees. On the left side, we could leave it like that, or if we wanted to, we could call that tangent 50 degrees times d. Okay, so our equation is linear, d to the first. So if we have equations that are linear, we want to get our variable terms on one side. If it doesn't have that variable, we want it on the other side. So let's move this term to the other side. So we're going to take it away from both sides. So take away tangent 23 degrees times d on both sides. So on the left side, those are like terms. The tangent 50 degrees times d and the tangent 23 degrees times d. But we have to be careful because tangent is a function. So this would not be tangent of 50 minus 23 degrees times d. That would not work. Now let's bring the other side down, the 443 tangent 23 degrees. What we can do on the left side is recognize that both terms have a d in them. That's a common factor. So if we factor out a d, we have tangent 50 degrees minus tangent 23 degrees. To get d by itself, we divide both sides by the parentheses. Again, we're not going to subtract those angles for the mere fact that tangent is a function and we can't subtract the inputs of functions. We can subtract the outputs but not the inputs. So those cancel, so we can calculate d. We can take that formula on the right side and put it in our calculator and get d. So we're going to do 443 times tangent of 23 degrees, and we're going to divide that by the results of, so parentheses, tangent of 50 degrees minus tangent of 23 degrees, close parentheses. So we're dividing by whatever that parenthesis is. That parenthesis on bottom comes out to be 0.767, so forth. So when we do the numerator and divide by that parenthesis, we get about 24.3. And I'm going to type that in again just to be on the safe side. Make sure I didn't type anything in the wrong way. And I have a feeling that I did. Because the second time I got 245, which sounds right. So So third time's a charm. Let's check it, make sure. Where I need an actual calculator because typing it in on my computer screen is not the easiest thing. So 245. Our original distance that we were given was 443 feet, so this will be in feet. But D is not what we're after. We're after H. But notice when we isolated H, we have two expressions that give us H. So I'm going to use this. If we know D, H is D times tangent 50. So whatever I just got for D, and in fact, I'm just going to leave that value in my calculator, and I'm going to multiply that times tangent of 50, and that gives me 292. So I have a height of 292 feet to the top of that tower.